Forget sharks, forget orcas entirely. There is a hunter in the open ocean that dives deeper than almost any fish its size, that keeps its brain and eyes running warmer than the freezing water around it, and that carries a blade on its face, harder than the hull of the boat trying to catch it. No teeth, no armor of scales, just speed, depth, and one very unusual weapon. This is the swordfish, one of the most singular and least appreciated hunters in the entire open ocean. And here is the part that almost nobody talks about. That same blade has, on more than one occasion, ended up buried inside the metal of a research vessel, hundreds of meters below the surface, in total darkness. We are not going to explain that particular story right away. Keep it in mind because we will come back to it roughly halfway through this video, once we understand exactly what makes this animal so unusual in the first place. Swordfish, scientifically known as Xiphias gladius, are the only living species in their entire family. People often lump them together with marlin and sailfish under the general label of billfish, but the resemblance is mostly superficial. In marlin and sailfish, the bill is round in cross-section, closer to a rapier. In swordfish, it is flat and wide, shaped much more like an actual blade than a spear. And the lineage behind that blade is genuinely ancient. Fossils of long-snouted predators built along similar lines turn up in rock layers tens of millions of years old, preserved well enough that researchers can still make out the same basic blade and torpedo shape we see swimming in the ocean today, which tells us that this basic body plan, a torpedo-shaped hunter with a flattened blade up front, worked so well that evolution barely touched the formula for an enormous stretch of time. To put that age in perspective, while many marine species we think of as familiar today have a fairly recent evolutionary history, the lineage behind swordfish was already swimming in ancient oceans long before some of the mountain ranges we now consider geologically old had even formed. And unlike marlin or sailfish, which share a separate family and keep scales, teeth, and pelvic fins into adulthood, swordfish are so evolutionarily isolated that they make up their entire family on their own, a fairly rare situation in nature, where most species have at least a few obvious close relatives still around. There is another oddity hiding in this animal's biology that most documentaries skip entirely. Baby swordfish are born with normal teeth and normal scales, just like the vast majority of bony fish. But as they grow, they lose both. An adult swordfish has smooth, almost scaleless skin and a completely toothless mouth. It's a strange contradiction worth sitting with for a moment. One of the ocean's most physically imposing hunters, stripped of the two features, teeth and scaly armor, that most people would assume any serious predator absolutely needs. In other words, this is a predator that quite literally disarms itself from the inside as it matures, and ends up relying on a completely different weapon to survive. Its coloring isn't accidental either. A dark, almost blue-black back blends into the depths and darkness when seen from above, while a lighter belly makes it harder for prey below to spot it against the faint light still filtering down from far above. A camouflage pattern common among large open ocean hunters, though in swordfish, it's paired rather unusually with an actual physical weapon capable of finishing the ambush in the final instant. That weapon does not work in isolation, though. Swordfish are one of a very small number of fish on the planet with their own internal heater. Near the eyes and brain, they carry specialized tissue capable of generating heat and holding it locally, raising the temperature of those organs several degrees above the surrounding water. Picture jumping into a cold winter sea and having your entire body chill down, except your eyes and part of your head, which somehow stay warm as if wrapped in an invisible heating pad. That is roughly what this system does for a swordfish, letting it keep sharp vision and fast reflexes even in the coldest depths of the ocean. Most fish are cold-blooded in the strictest sense, Their body temperature simply tracks whatever the surrounding water happens to be, with no active regulation at all. A swordfish, instead, has evolved a narrow, highly efficient solution to the same problem human divers face in cold, deep water. Keep the most sensitive machinery in the body warm, even if nothing else gets the same treatment. It's worth pausing on how a swordfish actually perceives the world, because its senses are just as specialized as the rest of its body. Its eyes are enormous relative to its body size compared to most fish of similar dimensions, an adaptation directly tied to hunting in near total darkness at depth. That eye heater wouldn't do much good without eyes capable of squeezing every bit of use out of the scarce light available hundreds of meters down. So the two adaptations, oversized eyes and localized heat, really function as one combined system. Its hearing, by contrast, seems more limited than that of many other large pelagic fish, and it relies more heavily on the lateral line, a sensory system running along the skin that detects vibration and pressure changes in the water, useful for sensing a nearby school of prey even before it comes into view. The reason it needs any of this comes down to lifestyle. During the day, swordfish typically drop down to 500, sometimes 800 meters or more, where squid and deep-water fish hide in total darkness, their main prey. Few environments on the planet shift as dramatically over a single day as the water column a swordfish passes through on this routine. Sunlight, pressure, temperature, and the mix of species around it can change almost completely between its daytime depth and its nighttime position near the surface, all within the span of a single 24-hour cycle. At night, they rise back toward the surface, tracking the same prey as it migrates upward. For most fish, that kind of daily elevator ride through wildly different water temperatures would be a serious problem. Vision and reaction speed both suffer badly in the cold. Not for the swordfish. Thanks to that internal heater around its eyes and brain, it stays an effective hunter no matter how deep it goes. This is a good moment to pause the story for a second before we go any further. Recommendation algorithms tend to show a brand new channel to a given viewer exactly once. If you scroll past this video without subscribing, there is a real chance this channel simply will not show up in your feed again, and you would miss stories like this one about deep-sea hunters, biological heaters, and record holders most people have never heard of. If this kind of thing interests you, now is the moment to hit subscribe. And while you're at it, drop a comment with the next marine species you would like to see covered here, whether that's another deep water hunter or something closer to shore entirely. Now, back to how this animal actually hunts, because that is where things get genuinely strange. Unlike marlin and sailfish, which often use their bill like a rapier to spear prey outright, swordfish tend to use their blade more like a saber. They charge at high speed into a tightly packed school of fish or squid and deliver a sharp, sideways swipe of the head, stunning or injuring several targets at once, then calmly circling back afterward to pick off the wounded. This tactic makes the most of a single pass through a dense group of prey, letting one swordfish disable several fish or squid at once, rather than expending the energy to chase down one target at a time. An efficient strategy for an animal that hunts entirely alone, with no pack members around to help corner prey. This kind of sideways strike takes real coordination between vision, the nervous system, and the muscles of the neck and head. A badly timed swipe could burn a huge amount of energy for nothing. So every charge appears to be calibrated with a precision that still surprises researchers studying this hunting behavior through underwater cameras and field footage. Estimates of how fast a swordfish can actually move during one of these charges vary enormously, and always have. Older figures floated numbers as dramatic as 90 or even 100 kilometers per hour. More recent and more careful studies put the real figure much lower, somewhere in the range of 30 to 40 kilometers per hour over short bursts. That gap is not surprising once you consider how hard it is to measure the precise speed of a wild animal in open water. So treat the more dramatic historical numbers as rough folklore rather than confirmed record. Even the more conservative modern figures, though, would still put a swordfish well ahead of an Olympic swimmer and comfortably in the same range as some of the fastest sharks in the ocean, which says something about how much raw power is packed into that streamlined body. An adult swordfish can stretch past 4 meters in length. Some records put it beyond 4.5, with a weight that, depending on the estimate, can reach 500 to 600 kilograms, roughly comparable to a small car. That weight, spread across a long, streamlined body built for speed rather than bulk, is part of why swordfish hit as hard as they do during a charge. All that mass moving at once behind a single, rigid point of contact.
On some individuals, the blade itself can exceed a meter in length, close to a third of the animal's entire body. To make that proportion easier to picture, imagine an adult human with one outstretched arm that, on its own, measured a third of their total height. That's roughly how disproportionate and how effective as a weapon the swordfish's blade is relative to the rest of its body. The internal structure behind that blade has actually drawn attention from engineers as well as biologists. Its strength comes not just from a hard outer layer, but from the way load is distributed through the bone along the full length of the blade during impact, which keeps it from shattering at high speed. Understanding that kind of natural shock-absorbing structure has real potential value outside biology in the design of impact-resistant composite materials, the same underlying engineering problem engineers face when trying to build something light enough to move fast, but tough enough to survive repeated hard impacts without cracking. That same cross-disciplinary curiosity applies to the eye and brain heater, too. Understanding how a fish generates and holds localized heat so efficiently, without anything like a mammal's circulatory system built for the job, has attracted interest from researchers working on small-scale heating and insulation technology far removed from marine biology. But it's not just the blade that has caused problems for people over the centuries. Long before industrial trawlers existed, entire coastal communities built parts of their economy around the seasonal run of swordfish, hunting them with harpoons from small boats. Harpooning swordfish required a specific set of skills passed down within these communities. A lookout would spot the fish basking near the surface, the boat would close in quietly, and a single, well-placed throw from a small platform, often extended off the bow, was the difference between a successful catch and a fish that simply vanished back into deep water, often in a matter of seconds. And within those communities, stories about pierced hulls have circulated for generations, with real variation from coast to coast. A frightened or pursued swordfish leaps clear of the water, and its blade drives straight through the wooden hull of a fishing boat, sometimes injuring the people on board. These are not baseless legends. They are documented episodes within the history of small-scale fishing along both the Atlantic and Pacific coasts. And they explain why, for generations, swordfish were treated not just as valuable catch, but as an opponent capable of striking back without warning. In some of these accounts, the boat came back to shore with the blades still lodged in the hull, physical proof that fishermen kept as evidence of what had happened, and pieces of it can still be seen on display in a handful of coastal museums today. Sections of ship timber punched clean through by a single piece of bone. That kind of physical evidence is exactly what has let naval historians separate these incidents from ordinary fishing exaggeration. These aren't just stories that grew with each retelling. They're physical objects that document the real force behind the impact. And it seems to be doing something similar on rare occasions in a very different setting entirely, which brings us back to that submerged research vessel we mentioned at the start. That reputation as a formidable opponent spread well beyond fishing communities themselves. Over the 20th century, the struggle between a lone angler and a massive open ocean fish
became a recurring theme in maritime storytelling. And it's worth noting that in the best-known piece of fiction built around exactly that kind of duel, the fish at the center of the story is a swordfish, chosen precisely for that combination of strength, endurance, and danger, a reputation this species had already earned among real fishing crews long before it ever made it onto a page. Sport fishing clubs around the world have spent decades carefully documenting exceptional catches of this species, and international competitions built specifically around swordfish still draw anglers from around the world every year, drawn by the sheer difficulty of locating a fish that lives alone and at real depth, combined with the reward of a genuinely massive trophy. First, though, let's talk about where all of this actually happens, because the range of this animal is remarkable. Swordfish live in nearly every warm and temperate stretch of ocean on the planet. The Atlantic, off the Americas and Europe, the Pacific, the Indian Ocean, even the Mediterranean, where a partially distinct population exists due to the particular currents and temperature patterns of that enclosed sea.
That kind of breadth is unusual even among large pelagic predators, most of which stay tied to a specific ocean basin. Swordfish, by contrast, seem comfortable almost anywhere the surface water is warm enough, and the depths below hold enough squid and small fish. That flexibility also shows up in how the species is managed. Because it crosses so many national and international boundaries over the course of a single migration, no single country can realistically regulate it alone, which is exactly why multiple regional fisheries bodies exist just to coordinate swordfish quotas across entire ocean basins. Researchers tracking individual swordfish with satellite tags have recorded migrations spanning several thousand kilometers in a single season. The same fish might spend part of the year in subtropical water, then relocate to a cooler but food-rich zone along the border between a warm current and a cold one. Some of these tracked individuals have crossed entire ocean basins over the course of a year, moving from one hemisphere's summer feeding grounds toward a completely different region once water temperatures shift, which means a single fish can end up covering a range most people would associate with an entire migratory bird population, rather than one solitary hunter. Journeys like that demand more than stamina. They require genuinely precise navigation, and how exactly a swordfish manages that is still not fully understood. Sensitivity to Earth's magnetic field or to temperature gradients in the water has been proposed, but there is no confirmed answer yet. The technology behind this kind of tracking is far from simple either. The satellite tags attached to fish like swordfish have to survive the pressure of dives hundreds of meters deep, release automatically after a preset amount of time, float to the surface, and transmit months of accumulated data on depth, temperature, and approximate position before the tag itself is ever physically recovered. Thanks to this relatively recent technology, scientists have been able to reconstruct movement patterns for an animal that, by nature, spends most of its life far outside the reach of direct human observation. When it comes to reproduction, swordfish belong to the group of broadcast spawners. Females do not incubate eggs or build nests. They simply release an enormous number of eggs directly into open water, by some estimates, several tens of millions in a single season, drifting freely with the current until fertilization occurs, which males fertilize on the spot. Interestingly, not every region where swordfish live also serves as a spawning ground. Females tend to gather to reproduce in fairly specific warm water zones, and in some basins, such as the Mediterranean, researchers have identified relatively small, well-defined spawning areas, which makes those spots especially sensitive when it comes to designing protection measures, since a single season of intense fishing right there, at exactly the right time of year, could have an outsized impact on the next generation of the species, potentially setting back years of otherwise successful population recovery in that region alone. Out of those millions of eggs, only a tiny handful survive to adulthood. Practically anything larger than a swordfish larva, from jellyfish to other fish, will eat it without hesitation. It's a brutal numbers game. Out of the tens of millions of eggs released in a single season, the vast majority never make it past their first few weeks of life, and only a tiny fraction ever reach the size where they stop being easy prey for nearly everything around them. But the few that make it grow at an extraordinary rate. In its first year alone, a young swordfish can exceed a meter in level, one of the fastest growth rates of any open ocean fish. Fast enough that a young swordfish can effectively outgrow most of its early predators within a single year, simply by becoming too large and too fast to be worth the risk of chasing. Its diet shifts almost as quickly as its size. Larvae feed on tiny plankton. Juveniles move on to small schooling fish, and adults eventually take on large squid and fish up to half their own body length. That shift in diet over a single lifetime isn't just a minor detail. It forces a young swordfish to completely rework its hunting strategy within just a few short years, moving from chasing tiny, scattered prey to coordinating that precise blade strike against dense schools and sizable squid, all while its own body, strength, and eye heating system are still developing. Males rarely live past 9 or 10 years, while females, generally the larger sex, can live 15 years or more. That gap in longevity between sexes isn't unique to swordfish, but it matters a great deal for fisheries management here specifically. Since females take longer to reach reproductive maturity and live longer overall, they also carry most of the population's reproductive capacity, which makes protecting the largest, oldest individuals a very concrete priority for any well-designed conservation plan. Adult swordfish are solitary, unlike many other large pelagic fish. They do not form schools, preferring to hunt and migrate alone, sometimes covering thousands of kilometers in search of concentrated prey and favorable water temperature. That solitary lifestyle stands in sharp contrast to tuna, which often share similar migratory routes and feeding grounds, but travel in large, coordinated schools. A reminder that even among fast, warm-adapted open ocean hunters, there's more than one successful way to make a living. And here is another detail that rarely makes it into the popular story. Despite its size, speed, and weaponry, an adult swordfish is itself hunted by other predators. Orcas, capable of taking on nearly any marine animal, occasionally go after them, along with large sharks such as mako and great whites, animals that not infrequently carry marks on their own bodies from the fight their prey put up before losing. It's a useful corrective to the common assumption that an orca or a great white simply overwhelms anything it targets without consequence. Going after a healthy adult swordfish is closer to a genuine fight than an easy meal. Younger, still developing individuals face a much wider range of predators among large open ocean fish. Even facing a predator as formidable as an orca, a swordfish rarely goes down without a fight. And that same blade used for hunting can double as a last line of defense, which may be part of why many predators prefer to target young or weakened individuals rather than a healthy adult at full strength. It's a dynamic that repeats across plenty of other top marine predators. Even at the very top of a food chain, size and weaponry don't guarantee immunity, and the real deciding factor usually comes down to the physical condition of the individual at the moment of the encounter, more than the species involved. Swordfish are not entirely solitary in another sense, though. Like many large pelagic fish, adults are frequently trailed by remoras and other companion species that latch onto their bodies or swim close by, scavenging leftovers from a kill and gaining protection from a much larger neighbor. Their skin and gills also host parasites specific to this species alone. One more sign of just how old and isolated this evolutionary line really is. Over millions of years, entire species have specialized to live exclusively alongside it, something that simply does not happen with any other billfish.
Studying these specialized hitchhikers has occasionally told researchers almost as much about swordfish migration patterns as satellite tagging data itself, since some of these companion species only turn up in very specific parts of the ocean. These relationships, though quiet and far less dramatic than a hunt or a clash with a predator, are just as important a part of its biology. No large predator lives entirely apart from its environment, and swordfish, for all their reputation as solitary hunters, carry around them a small ecosystem of dependent species. Now, let's finally return to that research vessel from the beginning of this video. Records from the mid-20th century describe a specific incident involving a scientific submersible descending to nearly 2,000 meters in complete darkness, far below where sunlight reaches. According to those records, the hull took a sudden impact, and when the exterior was examined afterward, a swordfish blade was found lodged directly in the metal structure, forcing the crew to abort the dive and surface early. Researchers who have studied this kind of event still do not fully agree on the cause. It could have been a defensive reaction, confusion caused by the vessel's artificial lights and otherwise total darkness, or simply a miscalculation at high speed. What is clear is that this kind of collision is not folklore or dramatic invention. It is a documented part of the history of 20th century deep-sea exploration. What makes this particular episode so striking is the depth at which it occurred, nearly 2 kilometers below the surface, in a zone where water pressure is immense and where very few large animals venture at all. That a fish, however fast, ended up ramming a lit-up metal structure in an environment that extreme is still, decades later, one of the most talked about episodes among researchers who study large pelagic fish. Let's move on to some records and unusual facts that rarely make it into mainstream coverage of this species. Swordfish are widely considered, with all the caveats already mentioned about the accuracy of historical speed claims, among the fastest fish in the ocean. Among bony fish, they are also one of the very few species with a true localized heater for the brain and eyes. Something similar, though not identical, exists in a handful of tuna and shark species, but the placement and efficiency of this particular organ in swordfish is unique. And here is probably the least known record of all. Few fish carry out daily vertical migrations, consistently and for their entire adult lives, that cover a distance equivalent to 1.5 Eiffel Towers stacked on top of each other, every single day, for essentially its entire adult life, without the benefit of any mechanical assistance beyond its own muscles and that remarkable internal heater keeping its eyes and brain functioning through the temperature swing. On top of that, among all so-called billfish, swordfish are the only ones that completely lose teeth, scales, and pelvic fins by adulthood, a degree of anatomical stripping down not seen in any of their closest relatives within that loose grouping of ocean hunters. And a few sport fishing records add to the picture too. Exceptional catches documented in international competitions have topped 500 kilograms on more than one occasion, putting this species among the heaviest bony fish ever reliably recorded outside the large tuna group. There is a less pleasant connection between this species and humans, and it has nothing to do with attacks. It runs through the food chain instead. As a large, long-lived predator sitting near the top of that chain, a swordfish accumulates substances present in the ocean only in tiny concentrations, substances that rise over time from plankton to small fish, from small fish to squid, and from squid into the swordfish itself, becoming more concentrated at every step up that chain. We're talking mainly about mercury. That is why health authorities in many countries recommend limiting regular consumption of swordfish meat, particularly for children and pregnant women. Not because the fish is toxic in itself, but because, as a large and long-lived predator, it has simply accumulated more of these compounds than a small, short-lived fish ever could. That's also why health guidance on this point tends to focus on frequency rather than an outright ban. An occasional serving carries a very different risk profile than eating swordfish as a dietary staple several times a week over months or years. That accumulation is directly tied to human activity. Industrial pollution of the ocean with heavy metals, climate change reshuffling the traditional migration routes of prey species, and decades of intensive industrial fishing have left swordfish populations in very different conditions depending on the region of the planet. In some waters, where fishing is tightly regulated through strict quotas, populations have gradually recovered following steep declines toward the end of the last century. In other regions, overfishing remains an active and serious concern for international scientific bodies. Management of swordfish populations varies enormously depending on which regional body sets catch limits in a given ocean. In the North Atlantic, for instance, the species reached a clearly overexploited state toward the end of the last century, which pushed regulators to introduce stricter catch limits and seasonal closures in certain zones. Later data showed the reproductive biomass gradually recovering, a case frequently cited as evidence that well-applied fisheries management can reverse, at least partially, decades of overfishing. A rare piece of genuinely good news in a field where most stories run in the opposite direction. In other ocean basins, however, the level of monitoring and quota enforcement is far more uneven, and the state of local populations remains a genuine concern. The most common industrial fishing method today is longlining. Long lines carrying hundreds of hooks stretched across dozens of kilometers of open water. This method works precisely because swordfish hunt alone and at real depth, well below where conventional nets can reach. But it comes with a cost. Alongside swordfish, these hooks also catch non-target species, turtles, sharks, seabirds, which is why the last few decades have seen active work on more selective fishing technology, including circle hooks that reduce the odds of catching unintended species, along with changes to the depth and time of day at which lines are set to further cut down on accidental catches. Climate change adds another layer of uncertainty to all of this. As surface ocean temperatures rise and current patterns shift, the prey swordfish depend on, schools of small fish and squid, also move toward new latitudes or different depths, and swordfish tend to follow. That means populations considered stable in a given region for decades can start showing up more frequently somewhere they used to be rare, while declining in their historical range, which makes setting fair and realistic catch quotas an increasingly moving target, since data collected even a few years earlier can quickly become outdated as the fish themselves relocate. Beyond the biology, swordfish also occupy a notable place in the global seafood market. Its firm, mild-flavored flesh, with a texture closer to a cut of red meat than to most ocean fish, is sold fresh and frozen worldwide, often commanding noticeably higher prices than most everyday seafood. A premium that reflects both its limited supply relative to demand and the cost and difficulty of catching a fish that lives alone, far offshore, and at real depth, which makes it a genuinely important economic resource for fishing fleets in several coastal regions, and also one of the driving forces behind the fishing pressure the species has faced over recent decades. In the kitchen, that same unusual firmness, rare among open ocean fish, means swordfish is typically cut into thick steaks and grilled or pan-seared, much the way a cut of red meat would be. A culinary quirk that also helps explain why it turns up so often on restaurant menus, even in places nowhere near the coast. And we finally arrive at a final twist that rarely comes up in popular accounts of this predator. Swordfish are not just a spectacular hunter with a blade instead of a nose, but in a real sense, they act as a living indicator of the health of the open ocean. Because they migrate enormous distances, dive through dozens of layers of water at wildly different temperatures, and accumulate chemical traces of their environment in their tissue over years, studying individual swordfish actually lets scientists read the recent history of entire stretches of ocean, almost like tree rings, except here,
Instead of wood, we're looking at muscle tissue. And instead of annual rings, a chemical signature that shifts depending on where the fish fed and how water temperature changed along its migratory path. A living archive most people would never guess is sitting inside an ordinary-looking fish steak. Remove a predator like this from an ecosystem, even gradually, and the structure of entire open ocean food chains starts to shift. Squid and small schooling fish, freed from one of their natural predators, can multiply more easily, which in turn affects their own food base, plankton, and from there ripples outward, eventually touching the chemical makeup of the water itself and the ocean's capacity to absorb carbon. This kind of cascading effect, where losing a single predator ends up reshaping processes that seem completely unrelated to it, has been documented in other marine and terrestrial ecosystems. And it's a useful reminder that no major hunter occupies its place in nature by accident. In other words, the fate of one solitary hunter with a blade for a face is tied to the health of the ocean in a much bigger sense than it first appears. It's also worth clearing up a common misconception here. Despite its fearsome reputation, the swordfish lives in deep open water, far from beaches, so the real risk to swimmers is essentially non-existent. Its history of incidents almost always involves fishing or research vessels, never people in the water. That distinction tends to surprise people hearing about pierced hulls for the first time. The popular imagination tends to place danger close to shore, when in reality, this predator spends nearly its entire life dozens or hundreds of kilometers from any beach, in water where humans rarely venture without the protection of a boat. Maybe the most honest way to close this video is with more questions than answers. We still don't fully know why some individuals ram boats or vehicles, what the true limits of their dives actually are, or how their behavior will change as the ocean keeps warming over the coming decades. What does seem clear is that behind the popular image of a fish with a sword for a nose is one of the strangest, least understood predators in the entire open ocean. Every new satellite tag, every new tissue study, and every new documented encounter, however rare, keeps adding pieces to a puzzle that, after centuries of contact between this species and human fishing communities, is still far from complete. And the swordfish itself keeps swimming through that unresolved story, completely indifferent to it, exactly as it has for millions of years. If this kept you watching until the end, hit like, subscribe, and let us know in the comments which marine species you'd like to see covered next. Maybe it's time to head back into the deep, or maybe it's time to head towards shore, where some of the ocean's most venomous residents are waiting for their own turn in the spotlight.